Okay, this next thing's really hard. I won't blame you if you don't understand. When something goes up from left to right, we say it's increasing. When something goes down from left to right, we say it's decreasing. And get this, when something doesn't go up or down from left to right, we say that it's constant. Wow. I need a break after that. No joke. This is the next concept. When something goes up from left to right, it's called increasing. When something goes down from left to right, it's called decreasing. And when something doesn't go up or down from left to right, it's called constant. Don't worry, I'll show an example. Okay, so this point up here is negative 4, 4. This point down here is negative 1, negative 2. This point here is 2, negative 2. And this point is 3, 0. We're going to go down and right forever there. Connect to that, that, and that. And this is a big old point right there. It does not continue or bend or go past or anything like that. We want to find the intervals where this is increasing where it is decreasing, and where it is constant. So increasing, as we go from left to right, where it go up at. Down, down, neither, 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 up. So it starts going up at 2, and it continues to go up until 3. That is the only interval where it is increasing, from 2 to 3. Now, this certainly looks like a point like these 4. It looks like a point. It is not a point. It is an open interval. It's saying that from 2 to 3, 2 is our first endpoint, 3 is our second endpoint. But since it's not square brackets, we're not including the endpoint. If you need to go back and review how to write things in interval notation, That is section 1.4 in the front of book extra lectures that I've been posting. You can review how to do interval notation from the previous classes. If you need me to direct you to it further, just let me know. So that's where it's increasing. Let's do constant next. Constant's easy. Where is it not going up or down? Well, right here from -1 to 2. That's the only place where it's constant. Why are we not using square brackets? Why are these open intervals? It's because at the point, we're not doing anything. Between the points, we can see we're going down, we're staying straight, we're going up, we're going down. But that's between the points. At the point, at this point right here, we're not doing anything. We're not going up, we're not going down. It's just a point. So that doesn't get included in where we're going up and in where we're going down. We go up to there, we go down from there, but at that point, we're not doing anything. And that's why we can't include that point. That's why there's no square bracket on the 3. Okay, decreasing from left to right here, the x value -4. And then we decrease to here, the x value -1. We have a second interval where we are decreasing. So we're going to join this. We're going to union it. Going down from 3 to infinity. Because it goes down and right forever. That means it goes right forever. That means it's going to be decreasing forever. That's how we look at a graph and figure out where we are increasing, where we are decreasing, and where we are constant. One thing I want to mention before we move on from this is that we can see we have no graph before -4. And then from -4 on, we have graph the whole way, forever and ever and ever. That means the domain of this is from -4 to infinity. That means we should have every interval from -4 to infinity except for the endpoints. -4 to -1, -1 to 2, 2 to 3, 3 to infinity. They're all accounted for. We've got it all. If we really wanted to get into it, and we're not going to, this can be defined by a piecewise function. If you found the equation of the line through these 2 points, the equation of the line through these 2 points, the equation of the line through these 2 points, and the equation of the line from here on, you could build a piecewise function in 4 pieces that gives this. So it's not just completely unrelated topics. They all feed into each other in some way. We're really just kind of picking a thing and digging at it, learning more and more and more about it. Okay. If we had just a parabola that opened upward, the vertex, the dip in the bottom, would be considered a minimum because it is the lowest point. If we had a parabola that opened downward, the vertex would be the highest point. You guessed it, we would call it a maximum. Minimum is the lowest point. A maximum is the highest point. Here, we can see that this would be the maximum of this sort of wave thing. It's the highest point. But what about this point? And what about this point? Sometimes a maximum is not a maximum. This is the top of a hump, top of a hill, just like this one, but there are other points higher than it. In its immediate area, though, if we kind of blocked out the rest of this, yeah, that sure does look like a maximum. So as long as we're not talking big picture, sure, it's a maximum. And the word we're going to use for this is relative because it's all relative. This would be a relative maximum because in its area, it's a maximum. See? And even though this one here is the maximum, same holds true. In its area, it's a relative maximum as well. So when we say relative maximum or relative minimum, that means any hilltops. Any hilltops. So what do you think we're going to call this blue point? Relative minimum. So when we're asked to find relative maximum, relative minimum, we look for the hills, we look for the valleys, we pick the points, whatever they are on the graph. And I don't really think we need to get into that too much further at all. Let's talk about symmetry. And what do I mean by symmetry? Well, if I draw a heart, and if I was a better drawer, artist, a heart would be symmetrical. I could fold it over and the left side would match the right side. Graphs, just like shapes, can have symmetry. But instead of, say, a circle where I can fold it vertically, I can fold it horizontally. Or a square, I can fold it vertically, I can fold it horizontally. Or a triangle, I can't fold that horizontally, but I can fold it vertically. This has vertical and horizontal symmetry as shapes. This one only has vertical symmetry, like the heart. Instead of doing it with just shapes, we're going to do it with graphs. So we'll have our graph, and let's say we have a parabola. A parabola has vertical symmetry. If we imagine putting a line down the center and folding it over, it would match up with itself. When we're on a graph, that vertical line in the center is the y-axis. So this is actually referred to as, there's that cursive again, y-axis symmetry. Now I said instead of a shape of a circle, I could turn that into a graph of a circle real easy by putting it on a graph instead of on nothing. Up to, right to, down to, left to. So let's say that's our circle. And again, if I was a better drawer, we can see that this also has x-axis symmetry. If we folded it along the x-axis, we can call it x-axis symmetry. Now, it kind of goes into what we were saying about the vertical and horizontal flips earlier. When we were flipping things from the top to the bottom, we were replacing the y coordinate with the opposite of the y coordinate. If there's x-axis symmetry, when I replace something up top and move it down below, it's going to be a point that already exists. The whole thing about symmetry is it folds over on itself. So that means if something has x-axis symmetry, anytime I take any y value, if I replace it with the opposite y value, I'm going to get something that's also on the graph. And it's going to work everywhere. So x-axis symmetry is taking our y, replacing it with the opposite of y, and seeing if it works. So let me use the equation of a circle, for example, because we know the equation. Let's say we had x squared plus y minus 1 squared equals 9. That is a circle. It has a center point of 0, 1, and a radius of 3. If I graph this, center of 0, 1. Oops, that's not right. 0 on the x, 1 on the y. And a radius of 3. 1, 2, 3 to the right. 1, 2, 3 to the left. 1, 2, 3 up. 1, 2, 3 down. So imagine it's a good circle here. Imagine I went through all the points. Since this circle was not centered, since it was moved up 1, since the center was at 0, 1, that means it does not have x-axis symmetry because it's no longer split exactly in half by the x-axis. Does it still have y-axis symmetry? Yes, it does. Because we can still fold it along the y-axis. But how can we tell? Well, if checking for x-axis symmetry would be checking that when we replace the y with the opposite of y, we get the same thing. Checking for y-axis symmetry is going to be moving things from one side of the y-axis to the other. So it's going to be replacing an x with the opposite of x. And we should get points that already exist. So for y-axis symmetry, we're going to replace the x with the negative x and see if it works. So why did I draw this out first? It's because for our procedure of determining x and y axis symmetry, we're not going to have the graphs to look at. Okay. So if I replace x with negative x, I'm going to get negative x squared plus y minus 1 squared equals 9. What happens when we square a negative? It becomes positive. No matter what that is in there, it's going to be positive. And look, I've simplified it. I got the same thing as the original when I replaced x with negative x. So that means I have y-axis symmetry. How could I check and see? If it had x-axis symmetry, we know it doesn't. We would replace y with negative y for x-axis symmetry checking. If we replace y with negative y minus 1 squared equals 9. Y minus 1 is not going to be the same as negative y minus 1. Therefore, these two things are not the same. Therefore, there is no x-axis symmetry. And if we, for instance, were looking at the graph of a circle centered at the origin, and again, pretend that my drawing is better than it actually is, we can see that we can fold it over the x-axis and it would line up with itself. That means it has x-axis symmetry. We can see that if we were to fold it over the y-axis, that it would line up with itself. We call that y-axis symmetry. And for x-axis symmetry, that meant that since all the points on the top would also exist on the bottom, and all the points on the bottom would also exist on the top, that we can replace y with negative y and get what we started with. It's a quality of any equation of any graph with x-axis symmetry. So if we have just something simple like x squared plus y squared equals 1, x-axis symmetry means that if we take the y and we replace it with negative y, we will end up back with what we started with. And since anything squared is the positive version, a negative y squared would end up positive. And this is, in fact, what we started with. So since it passes this test of replacing y with negative y and getting the same thing, that means it has x-axis symmetry. Replacing y with negative y, that's just saying any of our y values, the opposite also exists. So if it's on the top, it's also on the bottom. If it's on the bottom, it's also on the top. Okay, I know I was very repetitive there. You weren't crazy. I was saying the same thing over and over again because that's all there is to drive home about x-axis symmetry. Y-axis symmetry same logic. The stuff on the left exists on the right. The stuff on the right exists on the left. That means all x values also have their opposite. We're replacing x with negative x and seeing that we get our original equation back. So same equation, same circle. We know it has x and y axis symmetry by looking at it. We just did the algebraic test for x-axis symmetry. Now we're going to do the algebraic test for y-axis symmetry. We're going to replace x with negative x, or the opposite of x. No matter what we have here, when we square it, it will become positive. And this is our original. So it does, with algebraic proof, have y-axis symmetry. So we talked about these two last time. There is a third type of symmetry. And you're thinking, well, there's only two axes. What else can we possibly be symmetric about? It's going to be this point right here. We're going to call it origin symmetry. And the test for origin symmetry is that we're going to replace both x with negative x and y with negative y. And we're going to get the same thing back. Here, if we use the same equation we've been using, and we replace x with negative x and y with negative y, a negative squared is positive. A negative squared is positive. We do get the original back. So this does have origin symmetry. Great. What is it? What does it mean? This would be the same as taking your finger and holding it right down in the center, taking the top and spinning it to the bottom. Literally taking this and rotating it 180 degrees. We're not flipping it upside down. We are turning it upside down like a pinwheel. Here we can see that if we imagine doing that, take the top, spin it to the bottom, it would be the same graph. Now this only works because it's centered at the origin. We saw in that last example last time, if we start moving this up, down, left, right, It's not centered in the origin anymore. It's not going to keep both x-axis and y-axis symmetry. In fact, if it moves both up and down and left and right, that's going to mean it's not going to have any axes as symmetry anymore, because it would have to stay on the x-axis. So it couldn't go up or down at all to keep the x-axis symmetry. And it couldn't go left or right at all to keep the y-axis symmetry. Likewise, if we move this off the origin, we're not going to be able to spin the graph and get the same shape in the same spot. So the reason this works is with the 180-degree spin, anything in quadrant 1 would also exist 1, 2 quadrants away in quadrant 3. If we talk about these rules in terms of function, the x-axis symmetry, the one where we replace y with negative y, the original function would also be equal to negative f of x, the opposite of the original function. Remember, f of x is y. So we're replacing y with negative y and getting the same thing back. Y-axis symmetry, the one where we are trading x for negative x and getting the original function back. The original function back is what we get when we take x and replace it with negative x. So in function form, if this is true, if f of x equals the opposite of f of x, it has x-axis symmetry. If f of x equals f of negative x, it has y-axis symmetry. And for origin symmetry, it has to have both. Both things happen and we still get the original function back, both taking the opposite of the function and the opposite of the x. Y for negative y, x for negative x, y for negative y, and x for negative x. So I've been talking for a while now. It's only been these three things. Let's do all three of our tests for symmetry on some functions. Let's look at y equals the absolute value of x. Let's test this for x-axis symmetry, for y-axis symmetry, and for origin symmetry. For x-axis symmetry, we go y for negative y. And we want to test it back for the original. So we take our y, we replace it with negative y. How do we see if it's the same as the original? We solve for y. The original's solved for y. To solve for y, we would take the opposite of both sides. Y equals negative absolute value of x is not the same as y equals positive absolute value of x. So this doesn't hold up. It doesn't have x-axis symmetry. And this is the process. We need to find all three, so we do it again. Here's what we're starting with. Now for y-axis symmetry, we replace x with negative x. We see if it's the same as the original. If we replace x with negative x, we have the absolute value of a negative, but that's going to bring it up to the positive, because the absolute values of a negative and a positive are the same thing. So because of that fact, because we know these are the same, imagine -3 and 3, it'd be the same thing. It is the same as the original. So it does have y-axis symmetry. Does it have origin symmetry? We replace both y with negative y and x with negative x. We know the absolute value of the negative is the same as the absolute value of the positive. And just like we solved last time, y would equal the opposite of the absolute value. It is not the same when we replace both y with negative y and x with negative x. Not the same, no origin symmetry. And here we're able to verify these results because we know what this graph looks like. It's just y equals the absolute value. That's our v. Does it have x-axis symmetry? No. If we fold it down over the x-axis, it does not line up with itself. Does it have origin symmetry? No. If we hold the origin and spin 180 degrees, spin it upside down, it is not the same. But does it have y-axis symmetry? Yes. We see if we fold it on the y-axis, it does line up. Our results are verified. Let's do another. Trying to find something interesting that's not a circle. Let's go with y equals -2 x cubed. Well, we're going to test for x-axis symmetry. We're going to test for y-axis symmetry. We're going to test for origin symmetry. For x-axis symmetry, what do? We replace y with negative y. For y-axis symmetry, what do? We replace x with negative x. For origin symmetry, what do? We replace them both with the negatives. And after we do the replacement, we want to see if we can solve and get the original back. If we can get the original back, that means they're the same. That means it has that type of symmetry. So for x-axis symmetry, we would replace y with negative y, solve to try to get the original back. So take the opposite of both sides. Y would be 2x cubed. Y equals 2x cubed is not the same as y equals negative 2x cubed. So it does not have x-axis symmetry. Next, for y-axis symmetry, we replace x with negative x. So y equals negative 2 negative x cubed. A negative cubed is negative. Negative times negative is positive. Y equals 2x cubed is not the same as y equals negative 2x cubed. It does not have y-axis symmetry. This doesn't mean that we don't have origin symmetry. We still have to test for it. So we're starting again with y equals negative 2x cubed. We're going to replace y with negative y. We're going to replace x with negative x. Okay. A negative cubed is still negative. Negative times negative is positive. But here, when we solve for y, take the opposite of both sides. What are we going to get? Y equals negative 2x cubed. It will be the same as the original. Take the opposite of both sides. Negative y becomes positive y. Positive 2x cubed becomes negative 2x cubed. Y equals negative 2x cubed is our original. This does have origin symmetry. And how do we graph this? Can we verify that y equals negative 2x cubed doesn't have x or y symmetry, but it does have origin symmetry? Well, what's the parent function? The parent function is our cubic. It's the one that's shaped like that. A negative is going to flip it upside down. So instead of like this, it'll be like this. And since it's a negative 2, that means it's going to be a little bit steeper than usual. But that's going to be the general shape. It's not moved left or right. It's not moved up or down. And notice, if you were to imagine holding down the center of the graph and spinning it upside down, this leg lines up with where this leg was. And this leg ends up where that one does. And holding it down at the origin and spinning and getting the same graph back, that's the definition of origin symmetry. But we can see it doesn't have y-axis. It doesn't have x-axis symmetry. Okay, so that's symmetry. Next up, I want to talk about even and odd, but not even and odd numbers. Even and odd functions. Now we have to know about symmetry to talk about even and odd functions, because the definition of an even function and the definition of an odd function have to do with the type of symmetry that the graph has. The most basic example of an even function is f of x equals x squared. F of x equals x squared, we know, is your friendly neighborhood parabola. This graph clearly has a specific type of symmetry. It's not origin symmetry. It's not x-axis symmetry. It is y-axis symmetry. So an even function has y-axis symmetry. So from now on, we just know that. So I've given enough time here, maybe your mind started to think ahead. If an even function has y-axis symmetry, does an odd function have x-axis symmetry? Turns out no. The most basic odd function is f of x equals x cubed. We know what this looks like. We spent a whole day on our shapes. It's the cubic function. Doesn't have x or y-axis symmetry. Like we just saw in an example, a cubic, one that's still centered at the origin, has origin symmetry. If we hold down in the center and spin it upside down, we end up with the same graph we started with. So odd functions have origin symmetry. Numbers are either even or odd. Functions, on the other hand, don't necessarily have to be one or the other. Here's a function. By looking at it, we see that it has y-axis symmetry. So if we were asked, is this even, odd, or neither? Since it has y-axis symmetry, it would be even. Why? Because even functions have y-axis symmetry. What about this? It's a parabola. Does that make it an even function? Well, does this parabola have y-axis symmetry? It has symmetry with itself, but it does not have symmetry with the y-axis. If we fold it over, we would end up with a parabola on the other side. We don't have that in the original picture. This does not have y-axis symmetry. It is not an even function. It doesn't have origin symmetry either. If we spin it upside down, we end up down here. That's not the original picture. So it doesn't have origin symmetry. So it's not odd. It's not even. It's not odd. It's neither. Okay, our next example. Let's take a look at f of x equals 4x cubed minus x. So we're going to do the same thing again. First, we'll see if it is an even function. If we put f of negative x in, we get negative x's instead of x's. A negative to an odd power will be negative. So negative 4x cubed minus negative x is going to be plus x. This is not the same. So since f of negative x does not equal f of x, therefore, 3 dots means therefore, no y-axis symmetry, therefore, not even. That doesn't automatically mean it's odd though. Remember, it can be neither. So next we would check for odd. Unlike our symmetry tests, we don't have to test for x-axis symmetry because x-axis symmetry doesn't tell us anything. This question wasn't, hey, what type of symmetry do we have? It's, is it even or odd? The only types of symmetry that matter are y-axis and origin. So there's a reason that I did the even test first. It's because the origin also changes x for negative x. But instead of checking to see if we have the original, we check to see if we have the opposite. Remember, replacing x with negative x and y with negative y means that the y changes the whole function, the x changes as well. So if the original is the opposite of what we get when we have f of negative x, then it would have origin symmetry. Then it would be odd. So here's how we'll do this. If it's not even, if it doesn't have y-axis symmetry, we are going to factor out a negative. So we're going to factor a negative out. What do we get? The opposite of positive 4x cubed is negative 4x cubed. The opposite of negative x is positive x. Okay, so you have to be good with factoring going forward in this class. There'll be some review available to you but factoring and being taught factoring is not a part of this level of algebra. That is the previous classes. By this point, when I say factor out a negative, you should know how to get from here to here. Okay. And factoring is just multiplication in reverse. So you can check by distributing this negative back through and make sure we get here. The opposite of 4x cubed, negative 4x cubed, minus a negative gives us the plus. 4x cubed minus x, that's the original. That's the original function. And that means if I take the opposite of both sides, looky here, that's my negative f of negative x equals f of x. If I take the opposite of both sides, that's my definition. The original is what I get when I switch both. If I lost you here, going from the f to the f of negative x to the negative f of x, don't worry. If you followed that, great. I'm not going to do it that way. I'm not going to do it with the f of x's. I'm going to keep doing it the way you understood it a little bit ago. Thank you for watching. After my little experiment last lecture, I know how few of you actually are. I was imagining a full class. Instead, 2 out of 3 students are absent. So instead of writing it as the function this time, I'm just going to write it with x's and y's. We did replacing x with negative x. We saw it didn't have y-axis symmetry. It therefore isn't an even function. For origin symmetry, instead of all that f of x stuff, let's just do both. Replace y with negative y. Replace x with negative x. Cubing a negative makes the term negative. Minus a negative is plus. Multiply both sides by -1 to solve for y. So there's both sides unchanged, taking the opposite. On the left, the opposite of -y is y. On the right, distributing this negative, the opposite of negative 4x cubed is positive 4x cubed. The opposite of positive x is negative x. I did get the original back. I do have origin symmetry, which means this is an odd function. Next up, let's take a look at h of x equals 2x squared plus x. I'm going to run it through both ways, with the f of x stuff, in this case the h of x stuff, but also just using our basic rules. I'm going to do the basic rules first, and if you got it, if that works for you, great. If the function notation stuff works for you, that's great too. So first, I'm going to pretend we have y and x. I'm going to use our basic rules. For even, that's y-axis symmetry. That's replacing x with negative x. So replacing the x with negative x both places. Squaring a negative turns the term positive. Plus a negative is just minus. We already have y equals 2x squared minus x is not the same as 2x squared plus x. Doesn't have y-axis symmetry, it's not even. If I replace for an odd function, getting origin symmetry, which means both x for negative x and y for negative y. Here's our work for negative x already. If I replace everything with negative y, that's just going to change my y side. Now, if I want to solve it for y, whoops, that one there shouldn't be negative. That's our original. Multiply both sides by the negative. If I distribute, here's my y equals. Here I would have negative 2x squared plus x. Negative 2x squared plus x is not the same as positive 2x squared plus x. So I don't have origin symmetry. This one is neither even nor odd. Here's a trick you can use. Here, if we look at all the exponents, it's a mix of even and odd exponents. So that's going to be neither. Let me show this again. This time using the function notation method, replacing x with negative x. Hopefully this process is sticking for you. So h of negative x, we're going to go positive, negative, not the same. H of negative x is not equal to the original function. So not even. I'm going to go ahead and take the opposite of both sides. So again, just distribute a negative. This is also not the original function. I like that better than factoring out a negative, just taking the opposite of both sides. I like that better. We can work with that. Let's go ahead and do another round of these. Let's take a look at m of x equals negative x to the 5th plus x cubed. First of all, let's take a look at all of our exponents. They're all odd. Our shortcut's going to say this one's odd. Now, the second I add a +1 or something, this one doesn't have any x's, but if it did, it would be x to the 0. 0 isn't odd. So that one would be neither. We don't have a +1 here. We just have x to the 5th and an x cubed. Let's do our tests. Replace x with negative x. We do that everywhere. A negative to an odd power stays negative. So this is minus that negative x to the 5th plus a negative stays negative when we cube it. Minus a negative is plus. Plus a negative is minus. Not the same. Not the same. So it's not even. But if I take the opposite, it's negative x to the 5th, positive x cubed. That is the original. The original is the opposite of the x and the opposite of the y. Origin symmetry. Odd function. I like that method. That's clean. Takes us through even, gets us to odd if we need it.